Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR, NET, GATE, NT exam, PhD exam, SET exam, Tifr, Jest, IIT-Jam and other exams related to physical science. Okay, so guys, this is the fifth part of the series of CSIR NET Physics PYQs of June, November 2020. Okay. So also guys, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures which are going to help you to crack the exams related to physical science. Okay. Okay. So this is the fifth part of the series of CSIR NET Physics June November 2020 paper solution. Okay, so I'm going to start with first question of the day, and the question is, question first is, the Hamiltonian of a system the Hamiltonian of a system the Hamiltonian of a system of non-interacting and non-interacting particles and non each of mass and xi pi and xi are the momentum and position respectively of the ith particle. Average internal energy average internal energy of the system is, options are option A 4 by 3 kT, option B is 3 by 4 kT, K is the Boltzmann constant, okay, and C is 3 by 2 kT, and option D is 1 by 3 kT. Okay, so these are the options, guys. It's a good question. So the Hamiltonian of a system of n non-interacting particle, each of mass m in one dimension is given, okay, where lambda is a constant which is greater than 0. Pi and xi are the momentum and position respectively of the ith particle. The average internal energy of the system you need to find out. Okay, okay, it's a good question, guys, and I'm going to solve now. So we have been given Hamiltonian, that is H equal to sigma I equal to 1 to n pi square upon 2m plus sigma I equal to 1 to n So this is the Hamilton, right? I'm writing separately both the term. Okay, so I, and this is going to be lambda by 4, lambda by 4, lambda by 4, x to the xi to the power 4. Okay, xi to the power 4. Okay, so this is guys. Okay, so now we know guys for classical system down. Kinetic energy of that is sigma I equal to n, and particle E square upon 2m is half kT of classical particle. Okay, and non-interact. So kinetic energy we have got. Now we just have to get potential energy, and then we'll add with kinetic energy, we'll get the total average internal energy. Okay, internal energy. Well, so now we'll sigma I equal to 1 to n. Okay, I equal to 1 to n, that is lambda by 4 xi to the power 4. This energy is going to be, that is this is going to be equal to minus infinity to plus infinity. Okay, lambda by 4 lambda by 4 x to the power 4. Okay, e to the power minus beta, and e is this, right? That is potential energy, lambda by 4 beta lambda by 4 x to the power 4 d to plus infinity lambda by 4. Okay, so this is e to the power minus beta lambda by 4 x to the power 4 dx. Okay, so this is the potential energy or the energy of this part. Okay, so this we need to solve it. So this is the value of E, that is V, lambda by 4 x to the power 4 e to the power minus 4 x to the power 4. Okay, this value is this. Okay, simple. Now we will solve it. So there is a formula for solving, guys. Note down. So here what we can do is, because here you can see x to the power 4, x to the power 4, right? So this is a, because this value of x, whatever the value of x will be, that is going to be positive, right? It means this is even function, this is even function, so we can break the limit. So this is going to be 2 into integration minus infinity, 2 into integration 0 to infinity. Okay, we have broken the limit. So this is the 0 to infinity. Okay, lambda by 4 x to the power 4 e to the power minus beta lambda by 4 x to the power 4 dx. Okay, now we'll use a formula, guys. We have this formula, you need to note down. I have explained this formula in my math. Okay, x to the power m e to the power minus beta, or we can say e to the power minus alpha, e to the power minus alpha x to the power n dx. If we have this formula, so this is going to be integration 0 to infinity x to the power m e to the power minus alpha. Alpha is any constant, guys. It's going to be 1 upon n, this one, 1 upon m gamma m by n upon alpha, that constant, to the power m plus 1 upon n. Very important formula. Okay, you need to note down. Okay, so minus infinity to plus 0 to infinity x to the power m e to the power minus alpha x to the power n dx is 1 upon n, that's this power of x. Okay, and gamma m plus 1 upon n into alpha to the power m plus 1 upon n. Okay, so here in this case you can check, see here x to the power 4, and their alpha into x to the power 4 also there, right? So m and m are equal. So we'll take this e to the power x. These two will get cancelled. So lambda by 4. This is going to be lambda by 4, right? Upon, again will this is also same, guys. Same formula we are going to use here. X here there is no x to the power, right? So we can say we can consider x to the power 0, right? Because x to the power 0 is 1. So then this is going to be uh, 1 by 4 this is okay, this one 1 by 4 x 1 by 4 gamma 0 plus 1 by 4, because m x to the power m is 0, right? X to the power 0, right? Upon alpha is this one, beta lambda upon 4 to the power 0 plus 1 by 4. Okay, this is the one, guys. Very important step. Okay. So we'll solve it. So this 4 and this is going to get cancelled. Okay, this will be lambda by 4, and gamma this, right? Gamma this is going to be gamma 5 by 4. Okay, just wait, guys, let me write correctly. So this is this one, lambda by 4 into gamma 5 by 4. Okay, upon, this is going to be b lambda upon 4 to the power 5 by 4 upon, this is going to be this will right? This is going to be like beta lambda by 4 to the power gamma minus 1 by 4. Okay, no, just a 1 by 4, because this is, we have taken up, right? And this is going to be, and this is going to be gamma 1 by 4. Okay, now we'll solve it, and we need to know how to solve this gamma 5 by 4 and gamma 1 by 4, right? And we know that. I'll tell you how to do it. So this is going to be, v is going to be lambda by 4 into, this will take up. Okay, so this is going to be b lambda by 4 to the power this one. Just wait, guys. Lambda and beta. This is minus. This is just plus, right? So this is going to be 1 by 4 minus, this will go up, right? So this power is 5 by 4. It goes in numerator, then this will be minus power, right? So minus 5 by 4. Okay, upon this one. This is going to be, this is, now we gamma 1 by 4. Here we have gamma 1 by 4, right? Gamma 1 by 4. So gamma 1 by 4 is going to be cancelled. Okay, and into 1 by 4, right? So now the lambda, this is to the power minus 1, right? So the lambda will get cancelled, and beta value is kt, 1 by kt, right? So this value is going to be, and this 4 will also get cancelled, so this value is going to be 1 by 4 kt. Okay, so this is the value of potential energy, guys. Okay, okay, very good question. Now what we are going to do is, now the energy is going to be, average energy is going to be potential energy, kinetic energy, plus potential energy, right? So kinetic energy we have already know that is half kT, and this value is 1 by 4 kT, right? This is 1 by 4 kT. So if you solve it, so this is going to be 3 by 4 kT. Okay, 3 by 4 kT, and this is the answer, guys. Okay, 3 by 4 kT. So which option is matching, guys? Let me check which option is matching. Option B is matching, guys. Okay, option B is matching. So option B is matching. Option B. So 3 by 4 kT is the answer, guys. Okay, 3 by 4 kT. Okay, next question, guys. Next question is, it's a good question from electronics. Okay, so 10-volt battery. Question 2. 10-volt battery. A 10-volt battery. A 10-volt battery. A 10-volt battery is connected. 10-volt battery is connected in series. Connected in series to a resistor, and a capacitor, resistor and a capacitor C, as shown in the figure. As shown in the figure. Okay, I'll draw the diagram. Okay, the initial charge on the capacitor is 0. The initial charge on the capacitor is 0. Charge on the capacitor is 0. Initial charge on the capacitor is 0. The switch is turned on. The switch is turned on. And the capacitor is allowed to charge to its full capacity. The total work done by the battery in this process is. Okay, options are, option A is 10 to the power minus 3 joule. Option B is 2 into 10 to the power minus 3 joule. Option C is 5 into 10 to the power minus 4 joule. And option D is 47 into 10 to the power minus 2 joule. Okay, so this is the question. Very good question, guys, and very simple question. Okay, I'll make a diagram, then it will clear your all doubts. Okay, so the battery of 10 volt. Okay, and this is a switch. This is resistor. This is 47 kilo ohm. Okay, R, and this is capacitor whose full capacity is 10 microfarad. Okay, so this is the question. Now I'll read the question. A 10 volt battery is connected in series to resistor and capacitor as shown in the figure. Okay, so 10 volt battery is connected with resistor and capacitor C. Okay, capacitor C in series. Okay, as shown in the figure, this one. The initial charge on the capacitor is 0. Initial charge is 0. Okay, and the switch is turned on and the capacitor is allowed, and okay, switch is this capacitor is 0 and the switch is turned on and the capacitor is allowed to charge to its full capacity. Okay, so when we switched in, okay, when okay, so when switch is turned on, okay, the capacitor is allowed to charge to its full capacity. Total work done by battery in this process. So you need to find out total work done by battery, okay, in this process. So first, this is very simple formula based question, guys. We should know W. Total work done by the battery is W equal to QV. Okay, W equal to Q, to note down, guys. Okay, W equal to QV. W equal to QV. Okay, and also W equal to QV, and also we know that value of Q equal to CV. This also we know. This is also important. These two formula you should know. Work done is QV and value of Q equal to CV. So therefore W work done is going to be QV, and in QV, right? And that is going to be, in place of Q will write CV into V, right? So this is going to be CV square. So W is going to be CV square. Okay, and CV square means capacity. Its full charge is 10 microfarad, means 10 into 10 to the power minus 6 farad into V square. V square means 10 to the power 10 is volt, right? And 10 to the power 2. So if you solve it, so this is going to be, and this is 10 into 10 to the power 6, right? So this is power minus 3 joules. 10 to the power minus 3 joules. Okay, so very simple formula based question, guys. 3.5 marks question of CSIR net, June November 2020. Okay, so very simple question. This is we need to know the work done is equal to V is the in a 3-bit in a 3-bit in a 3-bit register, okay, Q1 and Q3 Q1 and Q3 significant bits most significant bits of the output respectively okay. Figure is given. I'll make figure in next page. Okay, if q1 q2 q1 comma q2 and q3 are set are set are set to 0 initially, set to 0 initially set to 0 initially, then the output after the arrival arrival of the second second falling clock second falling clock that is in short we say CLT. Okay, second falling clock CLK, second falling clock edge is option A is 001, option B is 100, option C is 011, and option D is 110. Okay, so this is the question. I'll make a figure, then your doubts are going to be clear. Okay, so this is like this. This is Q3 and this is Q3. This is D3, Q2, D2, Q1 and D1. Okay, D1. Okay, so this is Q1, this is Q2. Okay, and this is D input. D in equal to +1, and This is clock 1, clock, okay. This is clock 2. This is a clock. This is the 3-bit register, guys, okay. And below Q1, Q2 are least and most significant bits of the output respectively, okay. And then is Q1, Q2, Q3 are set to 0 initially, so they are 0 initially, okay. The output after the arrival of second falling clock edges, means after second clock pulse, okay. That you need to find out the output after the arrival of second falling clock edge, okay. Second falling clock edge or second clock pulse, okay. Very simple question, okay. So this is, these are Q1, Q2, Q3, right? So I'll make a table here: Q3, Q2, and Q1, okay. Okay, and second clock, so this will go here, right? 1, this will be 1, and this will be 0, okay. So options are given, guys, okay. So this is very simple. This is the register. The Q1 and Q3 are more 1 and 1, okay. So this is the answer. So 1 0 1 1 is the answer, guys. Which option is matching? 0 1 1, C option. C is the correct option, guys. I hope you have understood it. Next question I'm going to solve, that is the question number 4, okay. Question number 4. Question number 4 is, this is also from digital electronics question, okay. So the Boolean equation, the Boolean equation, the Boolean equation, the Boolean equation, that is y equal to a bar bc, okay, and plus a bar b c bar plus a b bar c bar, okay, and plus a b bar c, okay. So this is the Boolean equation given, okay, output of the equation, okay. Boolean equation, this is to be implemented, is to be implemented is to be implemented this is implemented using only 2 input NAND gates, okay. Using only 2 input NAND gates, okay. So the minimum number of gates required, okay. The minimum number of gates required is, okay. Options are, option A is 3, option B is 4, option C is 5, option D is 6, okay. So this is the question, guys. A very good question and very simple question. I'll tell you the trick for it as well. Okay, so the Boolean equation y equal to this is to be implemented. Okay, the Boolean equation this y equal to this is to be implemented using only two input NAND gates. Okay, this we have implemented using only two input NAND gates. Okay, so we made this by using only two input NAND gates. Okay, the minimum number of gates required, the minimum number of the gates required. Okay, that's we need to find out. So very simple. So first we have been given this output, right? We'll solve this output. Okay, so this output is going to be, we have given this y equal to a bar. We have to simplify that output as simple as possible. Okay, so we have to simplify this output. Okay, first, and then we'll proceed further. Okay, so this is a bar bc plus a bar bc bar plus a p bar c bar plus a b bar c. Okay, right. Now so we have to first simplify this boolean this output. Okay, as much as we can. Okay, so we'll take here a bar b common. Okay, a bar b common, so this is going to be c plus c bar. Okay, plus here we'll take uh, a b bar common, so this is going to be c bar plus c. Okay, and this value is going to be 1 and this value is going to be 1 because we know c plus c bar equal to 1. Okay, so this is going to be a bar b plus a b bar. Okay, y equal to this. Okay, so y equal to this means this is XOR gate, guys. Okay, XOR gate. Okay, XOR gate. This is XOR gate. Because this is like this a. Okay, this is XOR gate, guys. Okay, now so now we have to know how many minimum number of NAND gate is required to implement XOR gate or to make XOR gate. Okay, okay, so I'll solve it further. Okay, so I'll write a table for you so that you can easily solve this type of questions. Okay, so here we'll write in series. You need to note down. Okay, I'm going to write it in right. So this is going to be not AND or XOR XNOR. Okay, NAND and NOR. This you need to note down. Okay, and then here this is going to be this one for NAND. Okay, for NAND. For NAND. For NAND, and this is for NOR. Okay, so we'll write here 1, 2, 3, 4, 5. Okay, this will write 1, 4. Okay, this is 1, 2. This will remain 1. Okay, and then we'll this is 2, 3. We'll change this position. Okay, this is going to be 3, and this is going to be 2, and 4, 5 again will change this position. So this is 5, and this is 4, and this is 1, 4. So this is 4, 1. So this is the trick, guys. Okay, you should know. So for making NAND gate, for implementing NAND gate, NOT gate are required 1, not for NOT gate. So for NOT gate, right? For one NOT gate we can make it a NAND gate. For one NOR gate we can make a and we can make a for one NOT gate we can make a NOR gate, right? So similarly, for making NAND gate we need two AND gate. For making NOR gate we need three uh, AND gate. Okay. Similarly, for making XOR gate we need four NAND gate or and five NOR gate. Similarly, for XNOR we need five NAND gate, four NOR gate. Okay. So it's very simple. You'll write this in series: not and or, then XOR, XNOR, and NAND and OR. Now you have to number it from 1 to 5. Okay. And then this side 1 will remain 1. Then you need to change these two position. Okay. These two position. So 3 will go up, 2 will down. Okay. 2 will down. Okay. And similarly, you will change this 4 5 position. 5 will here, 4 will here, and then 1 4, and again you will change this position 1 4 4 1. Okay. So for making NAND gate, number of XOR gate required is 4. For making NOR gate, number of XOR gate is required is 5. Okay. So by if you know this table, we can easily solve this question. Okay. This is a this is a XOR. XOR means for making NAND gate. So how many for making XOR gate? Okay. How many NAND gate are required? Okay. This one. For making XOR gate, how many NAND gate are required? 4. How many NOR gate are required? 5. So for making NAND gate, how many for making XOR gate, how many NAND gates are required? 4. Okay. So for I'll not write here. I'll write. Okay. So number of minimum number of NAND gate required is 4, right? So this B is the correct option, guys. I hope guys you have understood it, and so how we are going to implement this, we can also implement it right there. So this is very good, very important thing. Okay, and I'll make it that as well. I'll show you how to make it. These are 4 NAND gate means like this, and like this. Okay, so these are NAND gates. This one. So we'll this is A, and this is B. So we'll take this here. We'll take this here. Okay, and then this is going to be here and here. Okay, this one. So this is A and B, and so this is going to be AB bar. Okay, AB bar. So this is going to be A bar, AB bar, AB bar. This is AB bar, and this is AB bar bar. Okay, similarly this is B AB bar bar. Okay, and this is going to be A bar B plus B A bar. Okay, or A bar B plus AB bar. A B bar. Okay, so this is XNOR case type. Okay, A. Okay, so this is the one, guys. So how many gates are there we have used for making this NAND XOR gate by NAND gates? 1 2 3 4. Okay, so this table is very important, guys. You need to note down. Very simple trick. Okay, so you can easily make XOR gate, AND gate, NOR gate, NAND gate or NOR gate by using this NAND and NOR gate. Very important question, guys. Okay, so I hope, guys, you have got the point. Okay, well, so this table I would request you to note down. Okay, very simple table. By that you can easily solve this type of questions. You don't need to make and then solve it, so it's going to consume a lot of time. Okay, in examination you need to solve question quickly. Okay, so that you can you will be able to solve more questions and you can get good rank. Okay, I hope you've got the point. Now next question I'm going to solve, that is question number 5. Question number 5 is this is also a good question. Okay, it's a conceptual question. The question is, the temperature variation of the resistivity temperature variation of the resistivity of four materials as shown in the following graph, following graphs. Okay, so I'm making the graph. Options are there. Okay, this is temperature and this is resistivity, guys. Okay, resistivity of the material rho. Okay, and this is the temperature T1 and this is temperature T2. This is resistivity, guys. I'll write it. Resistivity. Okay, this is a graph of the material between resistivity and temperature. Okay, and this graph is like this. Okay, like this. Next is option B. Resistivity and temperature. Okay, this is temperature T1 and this is temperature T2. Okay, and graph is like this, almost constant and like this. Okay, option C. T1, T2. Okay, and this temperature and this is resistivity and the graph is like this. Like this. Okay, and option D. This is temperature T1, T2 and T, this is resistivity. Okay, and graph is given like this. This is the graph, and this is like okay. These are the graph. Next is the material that would make the material that would make that would that would make the most sensitive the most sensitive most sensitive temperature sensor most sensitive temperature sensor most sensitive temperature sensor when used at temperatures between T1 and T2. T2 is okay. Options are option is A, option B is B, option C is C, and option D is D. Okay. So this is the question, guys. Very simple question. I'll read it for you. The temperature variation of the of of four materials. Okay, so the temperature variation of resistivity of four material as shown in the figure. So we have been there are four types of material we have been given, and we have been given the graphs for those material and the graph between temperature and resistivity. Okay, so this is the graph for first material. Okay, and the temperature variation of the resistivity of material. Okay, this is the second graph, second material, third material, and fourth material. Okay, now the material that would make the most sensitive temperature sensor. Okay, most sensitive temperature sensor. Okay, when used as when used at temperature between T1 and T2. Okay, in this range of temperature we used it. Okay, so the graph is so we have to just check the graph between this range T1 and T2, T1 and T2. Okay, so now we need to solve it. Okay, so very simple. It is asking the material that would make the most sensitive temperature sensor. We have to make a temperature sensor which is most sensitive. Okay, so by knowing the property of the resistivity of material. Okay, so I'll tell you the property of the material that resistivity, and then we'll select the correct option. Okay, okay, so for the temperature sensor, for the temperature sensor, this is a conceptual question. Okay, sensor for the temperature sensor, the variation the variation the variation in the resistivity in the resistivity variation in the resistivity variation in the resistivity of of the material of the material should be as large as possible as large as possible. Okay, as possible. okay, without any local minima or maxima, okay, without any local minima and maxima, okay. So for temperature sensor, for making most sensitive temperature sensor, okay, the variation in the resistivity, of the material should be as large as possible. Variation should be as large as possible, okay. The larger the variation, the larger the variation, that the sensitive material will be means the that uh, just wait a sec. Okay. So if the variation is larger, then the temperature sensitive will be more sensitive. Okay. So here you need to check. Okay. So there should be, so now what condition we know? We know that the variation should be as large as possible, and there shouldn't be any maxima or minima. Okay. Now on the basis of this statement, we'll check the graph. Okay. So check here. Here we can see there is a variation, but you can see there is a minima present, right? So this is not correct. Right? Similarly, this here you can check. There is a variation, very less variation. We can see we are checking between Q1 and Q2. Okay, there is a variation, but there is a minima as well. So this will also not consider. Okay, so these are not good material for temperature for making temperature sensor. Okay, now look at these two. Here you can see there is a variation, there is also variation, but there is a huge variation you can see. Okay, you can see the variation is huge, but here you can see this is all from here to here, you can see this is almost constant, right? And then this is what this statement is saying. Okay, for the temperature sensor, the variation in the resistivity of the material should be as large as possible without any local minima and maxima. Okay, so option option C is the correct option, because there is a variation, very huge variation. This may be also correct, but there is very less variation, right? If you compare there is a very huge variation. So this is going to be best material for making temperature sensitive sensor. Okay, so option C is the correct option. So this is the correct option, guys. I hope you have understood it well. Okay, guys. So I'm going to stop here. Okay, and remaining question we'll do in next class. And also, guys, I would request the students who haven't subscribed my channel yet, please subscribe